then we found that it is for the only LD calculation. Then the second table is we taken the U36 value, that is the Hubbard parameter. We take Hubbard parameter P and D parameter. For P orbital it is taken 3, D orbital 6. So we found that this the bandgap is matches with the experimental results. So how Hubbard parameter is chosen? So we calculated in the literature. We found that the P and D orbitals of some transition metals already studied. So Hubbard parameter, the literature value ranges from 5 to P value ranges from 5 to 10, and D value ranges from 2 to 5 and 6. So we tried with different Hubbard parameter values. So one literature is there 5.9 and D for 10. So we take it. It is found for 0.717. So in 3 6 values, it is matches with the experimental value. So we taken the Hubbard parameter values 3 and 6, and the further calculation is done with, that is this ultrasonic stereo potential with polynormal relativistic difference, which the LD plus U value 3 6 stands out for the further. So we start with the structural property. So these are basically 3 structures. First one is gallium nitride supercell, and the tandem of gallium nitride, and gallium side, tandem of gallium nitride at N side. So this is basically 3 general structure. There are also lot of structure. So the lattice parameter before geometry optimization, after geometry optimization we calculated. Before geometry optimization it is there, that is ABC value after geometry optimization, and this is the change in the values. So we found that the lattice parameter before geometry optimization is A equal to 6.462, B equal to 6.40, and C equal to 10.480. After we calculate the percentage area.
Also, you have not mentioned the units. So please mention the units. Otherwise, this numbers will not make any sense. Right?
Lattice parameter, but after
Yes, sir. So percentage in the lattice parameter, we found that is it is about 3% to 3% to 6% change is there. So it is structurally stable structures. Then we calculated the formation energies. This is the tabulation. In formation energy, this is the formation energy values. So we this is the lower part. Lower part is all about the gallium side of the, and above one are the nitrogen side of it. So minimum the formation energy, it is stable structure. So gallium nitride side doping transition metal is preferable. So all gallium side doping has low formation energy. The atomic radius or ionic radius of the transition metal is nearly equal to gallium side. So transition metal doped at gallium side of gallium nitride is more preferable and more stable. Then also 3 transition metal doped substitution at gallium side with vacancy we studied. Also here we found that there is the 3 docking at the substitution of iron in gallium side, and with n vacancy iron is exists lower formation energy. This one indicates it is the most stable configuration. Then formation energy of substitution of gallium side with the gallium vacancy. So we found that chromium side docking chromium, this one chromium, and the vanadium 3 vanadium atom docked with gallium vacancy. System exists lowest formation energy. Then we calculated the co-dot system, that is both chromium and manganese doping. We found that this one chromium side, so both are seeing the negative formation energy, which is both all these structures are stable. Then we calculated the bond length variation of dot gallium nitride system. So against on bond length in different transition metal structure found that is the atomic size and bond strength and structural stability. Under gallium nitride, this is the gallium and nitrogen bond is 1.966 angstrom, which is used for measure distortion in dot system. So gallium side doping measures dopant and N bond length is about 1.865 angstrom for nickel, and scandium is 2.039. This is the range of 1.8 to 2.039, and gallium tungsten bond length up to 3.1 angstrom. The replacement tends to cause the lattice construction in the gallium nitride network, lowering the bond length to 1.86 to 1.88 angstrom range. Gallium side doping brings about increased structural distortion and localized strain, which might play stronger roles in the magnetic and electronic properties of gallium nitride. Then we calculated the electronic properties. So these are the three band structure. As a band structure left, this is the band structure, and it is dot plot. So here alpha and beta both are there, but due to the symmetry, alpha and beta structure of the scandium side and the titanium side and the zinc of gallium nitride, all the alpha plots are symmetry with the beta plots. That's why the yellow color plot is not seen. So all three instances that we found that the alpha plot and the beta plot, alpha for the upstream and beta for the downstream, overlap entirely, signifying no spin polarization and accordingly non-magnetic downstream. The uniform absence of spin in the band structure and symmetric thus verifies the none of these dopant causes the magnetism in gallium nitride. So scandium doping and titanium and zinc doping gallium nitride shows the diamagnetic nature. Then after that, the vanadium, chromium, manganese, titanium, gallium nitride, we found that in the band structure, spin up, spin down bands are clearly non-overlapping. This is the first one is band structure of this one is the alpha and this one is beta plot. Then we found that there is non-overlapping in number of channel ranges, particularly around the Fermi energy level, demonstrating exchange splitting. Then the asymmetry also exists in the DOS plotted. We see that in the DOS plotted there is asymmetry in both the three cases, vanadium, chromium, and manganese cases, in which state distribution varies significantly between the two spins. This is upstream and downstream. There is the variation in states. For example, if there is greater intensity below the Fermi energy, we found that the Fermi energy greater intensity, while the spin down channels has peak position, various peak position and amplitudes. So all the above doping system, that is the vanadium, chromium, and manganese system, are spin polarized and shows magnetic. But manganese dot gallium nitride, the last one, shows greater spin exchange splitting, which can show the paramagnetic character. In upstream, this is the formula group, the dot is minimum, and for the down it is maximum at a Fermi energy level. So it is shows a greater paramagnetic character. This is the band structure of both upstream and downstream of iron rod and copper rod gallium nitride. Here also there is a spin asymmetry is there for in upstream and downstream cases. Clearly found that it is the Fermi energy at 0 level and it is shifted towards the conduction valence band, conduction band, the side of conduction band. And also we found that in Fermi level there is first part in Fermi level the density of state is minimum, and for the second part is density of load is density of states is mod. So this character, this both iron and cobalt doping, it is so half metallic characters, because the first one we clearly see that the for upstate band structure and density of state, it shows that it is semiconductor nature, and the for downstream it shows that it is semiconductor, sorry, metallic character. So it is metallic and it is semiconductor character. So for this system known as half metallic system. So a half metallic material that behave like a material for electrons with one spin orientation, while acting as a semiconductor or insulator for electrons with opposite spin orientation. So we can tell them that it is half metallic system of that. So there is a model known as Turner model for ferromagnetic based on the DOS satisfies here. So both systems are half metallic, spin polarized, and ferromagnetic. Also about the nickel and copper dot gallium nitride, there is also asymmetry is there for spin up and spin down state close to Fermi energy levels. It is a characteristic of spin polarization. Both the systems also moderate spin polarization establish the magnetic potential. Both systems do not show half metallic character because both the systems do not show half metallic character because there is both system is semiconductor character. So this is for chromium manganese. One chromium manganese two doping, that is 4 doping. For in 4 doping, we can also found that